And well, just I would like to briefly introduce our work in processing efficient materials under open atmosphere. And in particular, I will focus in this system where the active layer is composed of PTV7 and Pc7 As you may know, when we process these efficient materials in air conditions, we obtain lower efficiencies. And in our case, the drop in efficiency is clear, mostly due to a decrease in photocurrent and fill factor. And this morning, Dana also told us that PTV7 is indeed unstable in air, but we also, or it is also known that the processing additive used for the processing of this material system is also unstable. So although we use small quantities of this additive, the diode its instability may also contribute to the faster degradation. So our intention, our goal, was to find alternative additives to be able to process this material system or other. So the idea is not to work with this system, but just I want you to introduce an interesting tool to identify more stable solvents and additives. So in this particular case, this additive shows selective solubility for the fullerene. So in this case, we want to focus, or we want to find an alternative additive that also shows this selective solubility. This tool, you may know it, is called Hansen solubility parameters, where basically what we do is to plot in a solubility space, in a 3D space, different chemical contributions of the molecule, or molecules and solvents, so polar interactions, dispersion forces, and hydrogen bonding contribution. So, for instance, you can see the position in this solubility space of the fullerene, and how close chlorobenzene and diode are with respect to the target molecule. So our goal is to find, in this case, alternative additives or solvents that are close to diode, so they will behave in terms of solubility similarly as this additive. So basically, for those who are not familiarized, the closer a solvent or an additive is to the target molecule, the higher is the solubility affinity. So with this tool, we can identify which solvents are not useful or not recommended, and which could be useful in terms of solubility. We can, for example, look at these two solvents, but we have to also keep in mind that it's not only about solubility, but we also have to take into account the drying behavior. So we have to look also to the boiling point of the additive. So in this case, so considering this, from this set of chosen solvents, anisole would act more similarly as diode as compared to bromoanisole. So I wanted to introduce you this tool more than for that particular case, so with PTV7. The important thing here is that we can use this tool to identify more stable solvents or additives. Unfortunately, I still cannot show you results of solar cells fabricated with these proposed additives, but we are working on it. And that's all. Thank you.
Have time for questions, and now I would like to invite next speaker, Laura Karkolas. Not yet.
Good afternoon, everybody. First, I would like to thank you for giving me the opportunity to show you my results. So, as we all know, development of organic solar cells must be a trade-off between efficiency, stability, and low cost. However, we have to take into account different factors that can affect our devices, like, for example, oxygen and humidity. And of course, we need light. And our devices are made with polymers, so it's kind of a relationship, a love-hate relationship. So our question was, how can affect stability, the ambient conditions, and the radiation? In order to see how can this affect stability, we made different studies. One, trying to understand how affect the ambient condition, and the other, how to radiation condition affect our devices. Taking a look to the environmental conditions, we found that the degradation is due to radiation during the first hours. So you can see the IV curves and the S shape with time. And also you can see the evolution of efficiency and short-circuit current during time. So because this degradation is due to radiation during the first time, we thought, okay, what is the effect of these radiation conditions? And we found that if we represent efficiency or short-circuit current as a function of time, energy received, or number of photons, we found exponential curve fitting for all cases except for that organic solar cells without filters. So that gives us a first idea that mainly one degradation mechanism is occurring. Also, we found that the degradation is a function of wavelength because we use different filters, so trying to put only one wavelength in our devices. So for example, ultraviolet wavelength is the most stronger effect in this sense, but we can avoid that with the use of filters. However, in terms of filters, it's not too clear that we can to avoid, for example, blue radiation because it has a role in the photogeneration. So as I said, organic solar cell development must be a trade-off between these three components, but we also have to take into account several factors that can diminish the efficiency and stability of our devices. As the main result, we found that radiation effect is stronger than ambient condition effect, at least for the first hours of light exposure. Also, we found that the exponential fitting of power conversion efficiency and short-circuit current can give us first steps in order to try to understand degradation mechanisms. And finally, we also found that degradation is a function of wavelength. We can avoid, for example, ultraviolet with using filters, but not others like blue radiation. So that's all. Thank you. If you have questions, doubts, or comment, you can just go on us.
Thank you, Laura. And our next speaker is Jelly from Imperial College. We also don't have your signature. Is it okay with you to record the video? Okay.
How to switch on the laser? Yes, is that okay? Thank you. Good afternoon, everyone. I'm Jay from Professor James Durrant Group from Imperial College London. I'll
talk about something related to morphological stability of organic solar cells. So firstly, I'll just discuss a couple of examples that we just developed to enhance the morphological stability and hence the thermal stability of organic solar cells and elevated temperatures. The first one is the photochemical transformation of fullerenes and irradiation. Just like what Professor Manka has just mentioned, we just also observed that upon light exposure, and then the Pcbm molecules can form to dimers or high oligomers. And these dimers and oligomers, when blended into, in the blend, they can greatly suppress the crystallization of Pcbm and the high temperature thermal stress. So this graph we show for a range of different benchmark OPV blends, including the PCDTBT, PTB7, DPPTDT, and also P3T, we all observe that the after light exposure, then the crystallization is significantly suppressed, and also the morphological stability is enhanced. So with the increasing duration of light, and then we observe there's very great gradual enhancement in thermal stability as a function of the duration of low-level white light exposure. And we also performed more detailed studies about the mechanisms of how the formation of these dimers could potentially suppress the crystallization by whether it's related to the suppression of nucleation or the growth of the crystals, and also the different shape of these crystals for these different benchmark systems. So this is an example of what we have developed for morphological enhancement, and motivated by the previous work. So we just take advantage of the synthetic expertise at Imperial College London. This work is in collaboration with Professor Ian McCullough's group. So their group have made this cross-linked PCBM that is very nice analogous to the PCBM photochemical transformation. So with this in mind, we just also blend the polymer with a part of these Pcbm dumbbells. So once we blend into it, we just gradually increase the loading of the Pcbm. Then we just see significant suppressed crystallization, and also these enhanced morphology also translate into stabilized devices and 85 thermal stress. So. So this just gave you a quick introduction about several approaches we have developed. There are a few more as well. So if you are interested, then we're happy to discuss during the poster session. Thanks a lot. Thanks.
Thank you. You're all nicely in time, so we can now continue with the next speaker. I have to train his name. Stefarakat Karutedat. I hope that was okay. Did you have a signature? Good.
Oh, well, I'm Shafkat, working in India Nanociència, Madrid, as a PhD student with Dr. Larry Lewyer, and in collaboration with Tobias Sorman and Hans Joachim. Okay, our poster deals with effect of oxygen-induced degradation in P3HT, Pcbm, and silicon PCPDT-based solar cell. Well, a motivation behind our study is, you can see after photodegradation in synthetic air condition like 80% nitrogen, 20% oxygen, and 0% H2O, you can see that after 240 minutes of illumination, we are losing almost 60% of our current in P3HT and almost 70% or 60% in silicon PCPTBT. If you consider the relative of the optical density loss from UV visible spectra, it's relatively very less. Like for P3HT Pcbm, it is 2%, and for the silicon PCPTBT, it is 3.5%. So that means that we are the devices are absorbing our light as in pristine case, but they are not generating, or we cannot extract all the current produced by the device. So what we did was transient absorption studies. This is the kind of pump probe measurement. We excite the device and then see the effect of excitation by using a probe pulse. So we divided our measurement into our result in two parts: what's happening during the generation of our charge carriers and what's happening during the recombination. Since these measurements are done in films, there is no extraction because there is no electrode. And during the generation, you can see that the initial slopes are same for all degradation. That means that we are creating like 100% of charge carriers even though the devices are completely dead. There are some difference here that depends on the recombination, because after recombination, after degradation, your charge carrier becomes slow, and this part, the charge carrier is always starting to recombine even though we are generating there. So if you look at the recombination part, the first column is, the first column for the pristine polymers, and second column is for the degraded polymers. You can see that first column, the decay is quite fast, and second column, they're slow. This clearly says that something happened to their mobility. So we conclude that upon degradation, the mobility is getting slower, so that we are getting less current. So we fit all this our experimental results with the continuity model, where G is for the generation part, this, and Kr is for the recombination coefficient. This is the our polaron carrier density, and Cb, we introduced this term. This is for the background carrier density. We have to take care of that. And to conclude this, what we find that there is negligible loss in the generation of charge carriers. That means that our exciton dissociation is outperforming the effect of photooxidation. Is quite fast. And if you look at the recombination coefficient, it's getting decreased more than an order, and that's because of the energetical, maybe can be due to the energetical disorder of the active layer, and we can explain this by multiple trap and releasing model. And the third conclusion is background carrier concentration is considerably getting higher upon degradation, especially in the case of the low band gap polymer. So this means that if you have a lot of background carrier concentration, this effectively screens our built-in field, and which hinders the extraction of charge carriers. And yeah, that's the end of the talk. And if anybody interested in the results, yeah, I'm happy to discuss during the poster session. Thanks very much.
Okay, the next presentation is by Michal Dusa. So this presentation will be about photodegradation of inverted organic solar cells under various incident light spectra illumination using the LED light sources. So that saves you already, well, nearly a minute, I guess.
Good evening, my name is Michal Dusa, and I'm working in Wrocław Research Center, and I'm also a PhD student at Institute of Low Temperature and Structure Research. And today I would like to shortly present my poster presentation about photodegradation of inverted organic solar cells. What was the motivation for our research? We would like to investigate influence of energy photons and how energy of each photons have an impact to the stability of solar cells. We fabricated inverted structure of organic solar cells based on P3HT and Pcbm bulk heterojunction. We use glass substrate with 100 nanometers of ITO. We deposited zinc oxide layer by spin coating, and also active layer was spin coated, but under nitrogen atmosphere. Last two layers were thermal evaporated. We have to constructed very simple 3 LED light sources. We use some frosted glass as a light scattering elements to achieve better uniformity of light. And each of these light sources were calibrated using silicon solar cell, and each of them emits light power about 4.5 milliwatt per square centimeter. We measured the emission spectra of each light sources, and we can calibrate and time to time check the light intensity of these light sources. We also measured the PV parameters of samples under LED light sources and also under normal room light. One sample were kept in the nitrogen atmosphere without any shading. So we also as you can see, samples kept in the dark or in the under nitrogen atmosphere are quite stable, but samples under room light or even under LED light, in this example it's a green light, are much less stable. What is important, power of this LED light sources is very weak. It's only 4 milliwatts. What was the most interesting that each of LED light sources have the same impact on the stability. As you can see in this figure, that we recalculate days to the energy dose which was absorbed by our solar cells, and as you can see, that means that degradation mechanism depends on the energy dose, but not depends on the energy of photons. Of course, in this range, in our investigated range. Thank you, and if we have some question, I would like to invite you to the poster.
Thank you very much. Then we go to the last speaker of this session with the flash presentations, Giorgio Bardesa. It's about analysis of the series resistance and shunt resistance based on IV curve fitting of organic PV mini modules subjected to degradation under different temperatures and humidity conditions.
Thanks a lot for the kind introduction. Good evening to everybody. I am Giorgio Bardizza from ESTI, which is the European Solar Test Installation. And ESTI is based in Italy, in Ispra, and is inside one of the joint research centers of the European Commission, so is at the service of the European Commission, and is one of the testing laboratories, so we cannot produce or prepare any device, but we we are happy to receive devices to test. So please consider this also for your future record or not record devices. And in this sense, we participated in the SOFIA stability test organized by DTU, particularly by Suren, which prepared and distributed within 7 laboratories this type of P3HT Pcbm mini models. So you probably know better than me these devices, so I don't have to introduce you them, I think. Anyway, yeah, these are some details. And the goal of this study was to age these mini modules in 3 different aging conditions. So in ISOS D1, which is at ambient, let's say, laboratory condition. ISOS D2, which is at 65 degrees, so it's a dry, we call it dry chamber, dry heat chamber, and ISOS D3, which is standard damp heat chamber. And looking at the IV characteristic in time. So these were the measurements we performed at ST. And we submitted, obviously, this result to the organizers of the round robin, which mainly look at the comparison of these results within the laboratories participating in the stability test. After this, obviously there is a paper on this job, so we can, Suren knows that, and we can discuss about this in the future if you want. But with this measurement, we decided to look at them with more care, because we like them a lot. So particularly, we like this kind of evolution of the IV curves of the ISOS D3 device, so the one that was aged in ISOS D3, because the shape of the curve was really changing in a very continuous, more or less way. So we like to try to extrapolate more information from this curve. And in order to do that, we developed a fitting tool. We tried to fit these IV curves with 2 different electrical models in order to get some information about the series and shunt resistance out of them. So I will show you, if you come to my poster, that the one diode model was able to fit in a very good way the measurement of the ISOS D1 and ISOS D2 devices for all the measurement performing during the aging. While instead for ISOS D3 device, we're not able to use the one diode model because the curve after day 2 really start to have this famous S shape. So we couldn't use this one diode model, and looking in literature, we found this other, let's say, strange model where 2 diodes were facing back to back. And using this model, we managed to fit this S-shaped curve. And we believe we managed to get some, let's say, reasonable numbers from this fitting process. If you would like to know how the series and shunt resistance values coming from this fit evolve during the aging, I invite you to come to my poster and discuss in more details with me in the poster session. Thanks a lot for the attention.